What is the phase relationship between inductive and capacitive reactance? Imagine you're at a dance where two partners move in opposite directions. One partner pulls ahead while the other lags behind. In electrical circuits, inductive and capacitive reactance behave similarly, but how exactly do they relate in terms of timing? Let's find out. In AC circuits, reactance is what opposes the flow of alternating current caused by inductors and capacitors. It's measured in ohms but doesn't convert energy into heat like resistance does. Instead, it shifts the timing between voltage and current. Inductive reactance comes from inductors, which store energy in magnetic fields. Its value depends on the frequency of the AC signal and the inductance. The higher the frequency or inductance, the greater the reactance. Capacitive reactance, on the other hand, arises from capacitors, which store energy in electric fields. Its value decreases as the frequency or capacitance increases. Now, when you look at an inductor, the voltage across it actually leads the current by 90 degrees. That means the voltage reaches its peak a quarter cycle before the current does. Conversely, in a capacitor, the current leads the voltage by 90 degrees, so the current peaks a quarter cycle before the voltage. Think of it like a tug of war. The inductor resists changes in current, causing the current to lag behind the voltage. The capacitor, however, responds quickly, making the current surge ahead of the voltage. Because these effects are opposite, they are considered out of phase by 90 degrees. Inductive reactance makes the current lag behind the voltage, while capacitive reactance makes the current lead the voltage. When both are present in a circuit, they tend to cancel each other out because they are exactly opposite in phase. The net reactance is the difference between the two. At a specific frequency called the resonant frequency, the inductive and capacitive reactances are equal, and they cancel each other out. This results in a circuit where voltage and current are in sync, with no overall reactance. Mathematically, the impedance of an inductor is written as ZL is equal to JXL, where J is the imaginary unit representing a 90-degree phase shift, and XL is the inductive reactance. For a capacitor, the impedance is ZC is equal to JXC, indicating a negative 90-degree shift. The positive and negative signs show how the phase relationships are opposite. Understanding these phase relationships is key in designing AC circuits like filters, oscillators, and tuning systems. For example, in a series RLC circuit, the total phase difference between voltage and current depends on the balance of XL and XC. When they are equal, the circuit behaves as if it has only resistance, with voltage and current perfectly aligned. So, to sum it up, inductive reactance causes the current to lag behind the voltage by 90 degrees, while capacitive reactance causes the current to lead the voltage by 90 degrees. These opposite phase shifts are fundamental in how AC circuits work and influence how engineers control power flow, resonance, and impedance.